So how do we go about finding the area and the arc length of a sector? So I want to emphasize part over whole. Let's think of this sector here as a piece of pie. The area of this piece and this piece in general is a part of the entire pie. Think of the circumference as the crust. This arc length is this crust of this piece of pie is part of the entire crust. So I know that there are 360 degrees or 2 pi radians in a full circle. I also know that the area of the entire circle is pi r squared, and the circumference of the entire circle is 2 pi r. But we want just a little bit of that area. We want just a little bit of that circumference. We don't want the entire pie or the entire crust. So let's talk about area first. What if I just wanted half of a circle? Well, I could just take the area of the entire circle and multiply it by 1/2, and that would give me the area. Let's call the area of this sector A. I'm gonna divide by pi r squared for a sec, and I get area over pi r squared is equal to 1/2. Does this make sense? Well, the area is only half of the entire circle, and the pi r squared is the area of the entire circle, so I should get 1/2. I also know that the degrees that correspond with this circle, with the half circle, is 180 degrees, and if I divide that by the entire degrees in a circle, I also get 1/2. Both of these ratios are equal to each other, so I'm going to make a more general equation for the area of a sector. And that area of a sector, the ratio of the area to the area of the entire circle, is equal to the angle of that sector to the entire angle of the circle, which is 360 degrees. So as I'm increasing my angle, my area is going up too, which makes sense. As I'm going bigger and bigger, I'm getting closer and closer to the entire 360 degrees of the circle. And once I do get to 360 degrees, then this ratio right here just becomes 1, and my area is the entire circle, which would be pi r squared. So I'm going to solve this for A by multiplying both sides by pi r squared, and I get pi r squared, the area of the entire circle, times theta over 360. So in this equation here, I have the area of the entire circle, and it's being multiplied by a ratio. This ratio is probably going to be smaller than 1 if you're dealing with a sector. If you're talking about 360 degrees, then you're just doing the area of the entire circle. But for example, if this angle was 90, then I would be talking about a quarter of the circle. That means that 90 over 360 is 1/4 multiplied by pi r squared. The area of this would just be 1/4 pi r squared, which intuitively makes sense. Just like over here, it was pi r squared times 1/2. Is because I can clearly see that this is a quarter of the entire circle, just like this was half of the entire circle. This equation can be written in radians as well. Area equals pi r squared times theta over 2 pi. 2 pi because 360 degrees is 2 pi radians. The only difference is that your theta would also be in 2 pi. And so this simplifies to area is equal to r squared times theta over 2, because these pi's cancel out. So both of these equations can be used. You just need to make sure that if you're plugging in radians, you're sticking to radians. Like over here, I have 360 degrees. I cannot plug in radians to this equation. I will get a wrong answer. And over here, if I plug in degrees, my answer will be way too big. So this idea of part over whole works with a sector as well. Let's talk about an arc length of a sector. So if I have this circle and I want the arc length, let's call that arc length S. Well, the theta over 360 is not equal to area over pi r squared for arc length, but it's equal to your arc length over 2 pi r, not just 2 pi r, because 2 pi r is the circumference. And I know that the arc length is a part of the circumference. So you want to think of this as part over whole. I have part, which is my circumference, over the my arc length over the entire circumference. I have my angle, which is part of the entire 360 degrees of the circle. So I'm going to solve this for s by multiplying both sides by 2 pi r, and I got 2 pi r times theta over 360. This is an equation that you can use to find the arc length of a circle. And again, as I'm increasing my angle, I'm getting a bigger and bigger arc length, which makes sense because they're proportional, right? As I'm getting closer and closer to 360, I'm getting closer and closer to the entire circumference. This can also be written in radians, 2 pi r times theta over 2 pi, and this simplifies really good to s, my arc length, is equal to r times theta, because these 2 pi cancel out. So let's do a quick example problem. Let's say I have a circle with an angle of 30 degrees and the radius is 3 centimeters. So my area is equal to pi r squared times theta over 360, and let's just do the area first. So pi r squared, my r is 3, so this is 9 pi because I'm going to square my r, times theta over 360. My theta is 30, so I have theta over 360, 30 over 360, and that equals 9 pi times 1 over 12, which is equal to 3/4 pi centimeters squared. That is my area. Now, if I wanted to find the arc length, I know that my s, arc length, is equal to 2 pi r times theta over 360, part over whole times the entire thing, part over whole times the entire thing. So 2 pi r, well, my r is 3, so 2 times 3 is 6, so I have 6 pi times theta over 360. Theta is 30 over 360. This right here simplifies to 1/12, so 6 pi times 1 over 12 gets me pi over 2 centimeters for my arc length. So you want to think of this as part over whole. That's what I want to emphasize here. Whenever, if you forget your equation and you need to set it up again, think of, what am I dealing with, arc length or area? If I'm talking about the arc length, well, the arc length is part of the entire circumference, and that ratio is equal to the angle being part of the entire 360 degrees. Over here, the area is part of the entire area, which is pi r squared, and it's again equal to theta over 360.